a PA tap.
Yes.
Right, that's right.
Okay, well, for some reason, people did not read their many messages announcing this technical lecture, so I'm afraid that you have a very distinguished audience.
I do.
Could be, yeah. Okay,
Yes.
please, Peter, continue with your...
Okay. Well, thank you very much. Today I would like to take up the story that I took up yesterday and really work in detail on two aspects of music, especially in its relationship to mathematics, but also physics also. And I'd like to start out with this quote from Bourbaki from his essay on the architecture of mathematics, which you probably all know, but it seems to be very interesting as a starting point. Mathematics is like a big city whose outlying districts and suburbs encroach incessantly and in a somewhat chaotic manner on the surrounding country, while the center is rebuilt from time to time, each time in accordance with a more clearly conceived plan and a more majestic order. Tearing down the old sections with their labyrinths of alleys and projecting towards the periphery new avenues, more direct, broader, and more commodious. It can't escape anybody's notice that this is a kind of urban renewal metaphor for mathematics, and I suppose it's true, but the way he describes it, I'm hoping to persuade you, is a little chilling, and also for those of us that happen to love the old cities, kind of shocking, actually, that we're going to tear down the medieval city to make way for the more majestic order. I guess what I'm trying to do today is not only say that the history of mathematics and physics should be preserved in the way that we preserve the beloved ancient alleys of the old cities, but in a more radical sense. That is, that those ancient parts continue to be alive in the modern city. So it's not, Edmund Husserl, the philosopher, has a metaphor of sedimentation in which the previous layers of thought, especially in mathematics and physics, are presumed to be sediments or layers that are buried underneath the past, hence with the implication that they're inaccessible, or in Bourbaki's metaphor, that they've been simply bulldozed away to make way for much more commodious and majestic modern structures. Go ahead.
I thought that Bourbaki was a group of people.
It is a group.
So how can it then?
Well, the group produced this lecture in 1950, which is meant to be a kind of general introduction or preface to the whole work. It's probably Jean Dieudonné who has written this. It's my guess, but but Bourbaki. But at any rate,
I think it could be André.
Or André Vey. It sounds like André Vey to me. Yes, it has the attitude of André Vey, I think, much more. But it seems to me that what I would like to discuss today shows ways in which the history is erupting. It's not sedimented or buried, much less bulldozed. It's present continually. And it goes back to the starting point. Here's another wonderful illustration of the famous myth of the blacksmith shop, in which they are pounding away and making music, which Pythagoras kind of decodes to say, like, well, those hammers are dissonant because their intervals are not consonant. It's because all of the protagonists are immortal that they can't be buried or removed in a kind of urban renewal fashion. It's because the concepts that they represent remain permanent, and that even though the historical period in which music was so important, I'd like to persuade you to the formation of not only mathematics, but mathematical physics, mathematical science in general, but those concepts remain in play even today. Let's look at a few of them. Well, this is presumably in a blacksmith shop.
Everywhere people did it. This was Pythagoreans, so that was in southern Italy. Was it also done in Greece and in Turkey and so, or is it only Southern Italy.
Well, the story, I mean, since the historical Pythagoras is said to have lived in southern Italy, one presumes the story happened there, but you know, this is a myth. And I think it's well regarded as a myth. And also, it's also an impossible myth because already in ancient times, people started to say, like, wait a minute, if you have a 12-pound hammer and a 6-pound hammer, they don't actually produce an octave. In that sense, it's not just a myth, but an outrageously wrong myth. It was just so wrong that it was not just Vincenzo Galilei, the father of Galileo, who realized it was wrong and said it, but already people like Ptolemy said, like, wait a minute, there's something really wrong with this. On the other hand, it's not wrong that two strings of equal tension and double the length will sound an octave. So, you know, somehow there's a strange mixture of myth and numerological speculation that's overlaid over them. But it seems to me that one can pretty well kind of distinguish what is anybody that touches a musical string in the middle will realize that there's something going on there immediately. So let me just talk about a couple of concepts of Greek mathematics, just to sort of, because even though these are their terms, there still are words too. Arithmos is number. For them, it was number in the sense of integers, and integers larger than 1 and probably larger than 2, because the 2 was for many of the Pythagoreans a kind of dyad, not yet really a multitude. You only got to a multitude when you had 3 or more. A dyad was a kind of intermediate that Plato talks a lot about. And then the ratio, the logos, which is clearly related to lots of words having to do with logic and algorithm. Magnitude, megathos, is not a number. It could be the diagonal of a square. And hence, the famous proof shows that it's either unspeakable, areton, not able to be uttered rhetorically, or alogon, irrational. And the famous demonstration of that, which rests on the proof that the diagonal would have to be composed of both odd and even numbers at the same time. It is ironic that seeming contradiction is resolved by the concept of irrational numbers simply by allowing quantities that are magnitudes but not ratios, and hence sort of cutting the Gordian knot in the middle.
So what's the connection? The ratio and the logos is like more like a word? Or
A logos, it can be just a word, but it's also a ratio. And that's its kind of mathematical meaning, that it is a ratio. And so something...
All the same root.
Yeah.
Same root.
Right. So that something that is irrational is alogon, which means it has no word, i.e., you can't say in numbers, well, this is what the ratio is. It's unspecifiable in that sense. Yes.
Reasoning.
Yes, and logos is also the general word for reason, or for a reasoned account. In Plato, that's the word that he uses to say, like, if somebody's trying to give an explanation that's what we would say logical, also obviously a derivative of this word. But my point here is mainly that even though these are the historical terms, the thoughts that we have now are still deeply conditioned by all the ambiguities and all the penumbra of meanings that these words have. So that in that sense, they're still alive and their ambiguities are still in play. And the problems that the Greeks face, their realization that that there was this radical difference between geometry and arithmetic was what made them establish those two as separate sciences that they decided, that Euclid in particular decided, had to be kept rigorously separate to avoid any paradoxes in the foundations of mathematics. Paradoxes which still remain to this day, and I think the whole intuitionist controversy and all the controversies in the foundations of mathematics are still revolving around the problem of having numbers that are specified by an infinite number of digits and hence put in play infinity implicitly all the time. So those difficulties can't be buried or bulldozed away. They remain in the foundations of mathematics, and the fact that the words encoded, is not just a historical artifact, a kind of fossil, but the indications of a living wound in the body of mathematics, that once you decide that you're going to, as we see, that it takes a price has to be paid for each advance in mathematics that faces a fundamental difficulty in the way that the difference between irrational and rational quantities remains a kind of permanent issue. The interesting thing was that in each case you try to understand what does it take to cut the Gordian knot, or to solve what seems a complete paradox, because as I mentioned yesterday, the concept irrational number would have seemed to the Greeks wholly contradictory, as if they said non-number number or something like that. So the story that I'd like to talk about now is about how did it come to pass, or how did a series of mathematicians start to use that phrase and come to terms with it. And as I mentioned yesterday, the problem really came to a head when you were trying to take the tones, the ratios of 8 to 9, and divide up an octave into that. Boethius and the other ancient authorities decide, like, well, you can't really make an equal division because that involves taking a square root, according to this kind of Euclidean proposition in which you find a mean proportional that really divides geometrically a ratio in half. But that, of course, would involve the irrational quantity. So in ancient times, there were things like major and minor semitones where they said, well, we'll break the tone up into two slightly unequal parts, one a little bit bigger than the other, separate, whose difference is this Pythagorean comma, this kind of residue or leftover piece that appears in many places in music theory. But the problem is then you don't have, the semitone's been divided into two, but not to two equal parts. And you constantly have to decide which one you want. Certainly the piano would be impossible. You'd have to have two black keys or something to account for the fact that one would be the major semitone and the other would be the minor semitone. So it was in this kind of the musical question of musicians saying, especially I suppose those that played with fretted instruments, saying, well, I can make a geometric construction like this. I can put my finger right there or a fret right there. What's wrong with it? Okay. So, and as I mentioned yesterday, Michael Stiefel in this early book on arithmetic is the first person really to write down a square root and then whole numbers as if they were on the same plane. But the interesting thing is that Stiefel, even though he writes this down, was very uneasy about it. He goes on, I mean, he was probably the greatest mathematician, or German mathematician, at least of the 16th century. He introduced the term exponent, which is a pretty big thing. He was already using logarithms long before Napier. So he was quite an advanced thinker. But he, even though he started to say, like, well, in music, it seems as if you need to have a semitone in order to have scales and to have diatonic music that we're going to talk about in a moment. But then he at the last moment, he got cold feet, and he says, this is the passage. On the other hand, other things move us to a different assertion, namely that we are forced to deny that irrational numbers, he's the first person to write that phrase down, are numbers. Namely, when we might try to subject them to enumeration and to make them proportional to rational numbers, we find that they flee perpetually, so that none of them in itself can be precisely grasped, a fact that we perceive in the resolving of them, as I will show below. And he goes on to say, just as an infinite number is not a number, so an irrational number is not a true number as in hidden under a sort of cloud of infinity. So the cloud of infinity bothered him a lot. And it also bothered Kepler, who, as I mentioned, deals somewhat glancingly with algebra in his works, never really uses it, but is aware of it and writes down a few algebraic equations, says, well, I can see that these are very useful, but aren't they paradoxical in that their real meaning is an infinite series of decimals? Can't we avoid this by using geometrical means throughout? This is also Newton's thought throughout the Principia. Of course, he hated Descartes and hated Cartesian algebra, but I think he also had foundational questions about using quantities that in principle are unspecifiable. So he too preferred to use a kind of ancient geometrical way, so that the ancient separation between arithmetic and geometry was certainly in play through him. So it's very interesting. So Stiefel, even though he's the first person to use the word irrational numbers, doesn't like them. Finally says, well, they're not real numbers, certainly, or not numbers that you could put next to or in proportion with other numbers, because that was Euclid's master stroke. He said, you could have a ratio of two magnitudes. You can even equate that to the ratio of two numbers, but you can never, what we would say, cross-multiply them. You could never have the ratio of a number to a magnitude. And that was his brilliant solution for avoiding any kind of problem. And it worked very, very well, except that the need to construct algebra, that was one of the most pressing things that drew people to have to be able to allow kind of cross-multiplication to occur. So let's look now at another figure in the history, a very famous one. There's Girolamo Cardano, who, of course, the great art of algebra is one of the foundational texts in which the solutions of cubic and cubic equations and other things are put forward, and he tries to make a kind of whole. He finds himself using what we would say irrational numbers continually as part of the solution of these algebraic problems. Partly it has to do with the fact that algebra was a low-life, kind of a low-class science. At the time, it was part of commercial mathematics. It was not part of the ancient quadrivium at all. It was used for kind of popular entertainment. There would be kind of jousts where people would challenge each other with problems, and people would bet money. It was like a blood sport, really. And the famous stories about Cardano, Tartaglia, the issues about the priority of who really was the first to solve the cubic equation and who stole whose solution, come from this disreputable world of kind of condottieri that were sort of fighting with each other. But that also allowed, the fact that it was happening in a somewhat disreputable way enabled them to take certain liberties that were very, very important. In particular, to take liberties with the concept of number, which had been sacrosanct up until then. And it's very interesting that Cardano, during the time that he's writing The Great Art of Algebra, is also writing a book on music. So he's also facing the kind of musical problems. And in this passage, which is a kind of a mess, but an interesting kind of mess, he too is trying to figure out, well, how do you divide up a tone into two parts? And he actually makes a number of mistakes as he's trying to do it. And he says, like, well, maybe we could just sort of split the difference and say that half of it is 36 to 35, or maybe it's 35 to 34. And the upshot of it is, he says, well, the real answer is the square root of 72. But he knows that he's aware that that's somewhat illegitimate to do, but it's clear from this and from other passages that they sound nearly the same. That is, if you listen to these, if somebody plays these ratios to you, you can scarcely tell the difference, so that the difference between the absolutely pure sound of square root of 72, which is not a number, and various rational approximations to it is almost insensible. And so Cardano is ready to say, like, well, it's close enough. It's close enough for us to work. So we'll accept it with a kind of sensual indulgence that sort of led over the whole thing. And it's interesting that Stiefel was not, he wrote some songs. He was not just a theoretical musician, although his interest was mainly in the theory of music. Cardano wrote quite elaborate canons. His book on music shows quite a sophistication also of composition. The third figure I want to mention is well known in the history of music, but not so well known outside, a man named Nicola Vicentino, who became fascinated with the question not only of dividing the tone into two semitones, but of going into quarter tones. Here's a picture of him. And here's, so that in Boethius, who transmitted ancient music theory to the West, recorded that there were three different genera, or as it were, three different sexes of music in ancient times. There was diatonic music, chromatic music, and harmonic music. Diatonic music, here's an example. This is a Delphic paean. It's composed of a pattern of semitone, tone, tone. This is an authentic, this is from an ancient Greek source. So presumably it was the song that was sang to Apollo at Delphi. Let me just. So that was something of the sound of diatonic music. And diatonic music is mostly what we hear. It's a very, very, very common form of music even today. Chromatic music involved the use of semitones much more closely spaced together. The ancient pattern involved semitone, semitone, and a trihemitone, which is three semitones together. And I wanted to play this example of Luca Marenzio, which is a kind of very beautiful example. And when Boethius is describing it, he says that chromatic music is more colored, hence chromatic, in the sense that it's more sensual, more, and the sensual quality of this music. And this is basically just a rising chromatic scale. Oops. Just the rising chromatic scale, semitones. And the voice comes in. Solo et pensoso, alone and thoughtful, by Luca Marenzio. And that sound fascinated the composers of the time, and several of the pieces that I'm going to play this afternoon have to do with the power of the chromatic scale and its sensuousness. And chromatic music remains a very important part of our music. Much of romantic music is highly chromatic and derives its expressivity precisely from the power of the semitone with all of its implicit or explicit irrationality to move us. The third kind of music was praised by Boethius as being the most natural. This enharmonic, the Greek word for it, is harmonia, which means literally harmonious music. But it involves quarter tones. And so Vicentino in particular became fascinated with why was this music so powerful? Why did the Greeks do it? And why have we stopped having it? So for example, although he didn't have access to it, this is the only surviving fragment of the music of a Greek tragedy, music for, pardon?
Does it mean not harmonic?
Enharmonic meaning harmonic. So it's not enharmonic, but en. So, and then the Greek word is just harmonic, harmonia.
Yeah.
Somehow, when it came into Latin, that en got attached to it. But for instance, so here you can hear a piece with quarter tones that has actually survived from. And it has a very exotic and strange sound, but it's very interesting because it is the only access that we have to what a Euripidean tragedy actually sounded like. And it has not just one note, but there's an additional pitch that's in there that you can see in there. And there's lots of missing things in this fragmentary thing, but there's enough to give you an impression of it. So Vicentina became fascinated with this and got involved in a big controversy. In Rome, there was a performance. He was part of the musicians of Ippolito d'Este, the cardinal Hippolyta of the family of d'Este. And so there was a performance of a motet, and an argument ensued in which people asked whether or not enharmonic music had any place in the music of the present day. And Vicentino argued no, and there was a trial ensued. There was such a controversy, this went on for days, that they summoned a trial in the Vatican, presided over by this cardinal, and there were judges who were singers of the papal court. And as a result of it, they had this trial, which I think was probably kind of a mock trial, but Vicentino, in his account of it doesn't portray it as a kind of a joke. And anybody that knows anything about the history of sort of auto da fe and the Roman Catholic Church, it could be a little alarming to be tried by a cardinal in the Vatican. You just would worry about it. At any rate, the trial resulted in this sentence that he was wrong and he had to pay 2 scudi or something like that, some money. Probably everybody thought it was good fun, but Vicentino was furious. He was sure he was right. He was sure that enharmonic music was neglected, and he was going to find out, he was going to put it back on the map. He invented this thing called the archicembalo, which is a harpsichord that has the possibility of playing quarter tones, and you can see it has doubled keys, and there's his diagram of it there. So, and then he wrote compositions, and he tried to demonstrate it. And let me play this one composition here, in which he successively, in the different parts of the composition, he has all 3 genera: diatonic, chromatic, and then so here's the diatonic part. And the text is a kind of praise of the cardinal, of course. This is purely diatonic. Then the next part is chromatic. And then the last part is enharmonic, in which he praises the great deeds of Hippolyte, the cardinal, because he felt that, as in ancient times, enharmonic music was used for the greatest occasions and was patronized by the greatest figures, it should be patronized in his own time. there's quarter tones. So, I mean, it actually, there are kind of funny stories about how Vicentino tried to make everybody in the cardinal's household, including his friends, sing in quarter tones, and the results were what you can imagine, because it's very, very difficult to do. But the important thing was that as part of that, then, yes, please.
I don't understand anything. So chromatic I understand, and I can do that
Yes.
myself. Now, what is now enharmonic? Is that quarter tones?
Quarter tones, yes. Basically, the pattern is quarter tone, and then two whole tones.
Imposed on chromatic or not?
Say again?
Is it a refinement of chromatic?
Well, not exactly, because it involves intervals that have not been included in chromatic. Chromatic doesn't involve quarter tones, just
I'm
semitones.
saying refinement means including.
Yes.
Is the basis chromatic and then a fine structure which is enharmonic?
Basically, yes, although I think that the actual pattern, the ancient pattern that's specified, actually doesn't involve semitones, just quarter tones, and it's a quarter tone, and then two whole tones to span a fourth. So it is it's a fundamentally different pattern rather than a refinement of chromatic music. And the idea was that it would have a kind of power, that it would be appropriate for the tragedies, it would be appropriate for the most solemn music, and it would be separate, really a separate genus, not a subgenus of the chromatic. But it had obviously gone out of favor because already in ancient times this is just too difficult. People can't sing quarter tones. And so, but the mathematical problem was that it was already a problem, it's already a square root to get a semitone. And so to get a quarter tone, you need a fourth root. And so Vicentino, since he was so committed to having quarter tones, say like, well, we're going to have these irrational ratios in music. And he says, even though they disrupt, and he uses that phrase, even though they disrupt the texture of music, they're so important because they are maintaining a kind of ancient music that has been lost, which he is convinced that he's going to revive, and that is going to bring back a kind of era of greatness and glory that has been lost in modern times. Please.
There's a classical problem in terms of expressing these ratios as numbers, but technically it's not a problem, is it? Just
well, it is a problem.
Strings of
yes.
whose ratios are
one. You could set up. Let me just find out here. It's this picture. Sorry.
Just a diagonal square with the rope.
Something has happened here. Sorry. Josh?
Josh?
Oh, Trust. Anyway, there's something on the server. I don't understand.
Okay.
Hello? Yeah. Could you help me? Somehow it has fallen off of the... I think it tried to reach the server and had a problem. So, sorry, Nikita, let me go back to you. I mean, in the sense that you could make a geometric solution to the problem and find the location geometrically by doing a kind of analog of the Euclidean construction, means that you could find the note. But if someone said to you, what is that? What are the numbers of that note? You would be having to express an approximation to an irrational number.
Why do you need to express this if I just keep the key on the device?
Well, the key is not, because then the key has to be found through dividing up a string. You can no longer do it by counting string lengths. You have to do it by creating a geometrical diagram of the sort that had never been allowed in music before. Because music had always been based on 1 to 2, 3 to 2, 4 to 3. But the moment you start to say like, no, you can't count anymore. You just have to put your finger where this geometrical diagram indicates. It was a new departure that had never been allowed, and it seemed to step from arithmetic into geometry, from the rational to the irrational. But so great was the desire to have the expressive power that allowed that Vicentino and decided, like, okay, we've got to do it anyway, even though it's violating the canons of mathematics that were known to him, that he used as a musician. He thought that the needs of expression supervened and meant that he had to do it. I don't know if that's... Is that answering your, responding to your...
Look at, so if I just look at the diagonal of a square,
right,
I see root of 2.
you
So
see it,
if I'm an engineer, I can just make this square root of 2.
but it won't be the square root of 2. It'll be some approximation. It'll be 1.414.
Of course, but I mean,
But and we're so used to saying that's close enough. But in ancient mathematics, that was not, there was then an infinite difference between specifying that, thanks Josh, specifying it and having it, so that close enough was approximate. The idea that approximation was sufficient was unknown in ancient mathematics, and also even in modern mathematics leads to problems of, well, what does it mean to truncate numbers? I mean, as you know, there was an enormous controversy during the 19th century about whether the foundations of calculus and all the rest of it.
that's a separate, very interesting discussion.
Right.
Infinitely long discussion. But
Right.
By having a musical instrument,
Yes.
it's made of real things, which are never exactly
Right.
length or right tension or right thickness. We always use some kind of
Right, and we're used to that now because of physics. Because of Galileo. Galileo saying, well, the physical world is never going to be an ideal model, but this is all happening before Galileo. It's happening before people have the idea that the real world is going to give us an insight into the mathematical world. For them, things had seemed to go the other way around. The priority was in the ideal, and then the real had to somehow answer to it instead of the other way around. So the shift in mind that allowed mathematical physics to come into being and to say, even though in the physical world none of the laws are going to be perfectly observed because there's going to be experimental error, that will suffice. That will be close enough. The only place in which people had experienced that problem before was in music. And practical musicians were ready to do exactly what you said. It's just that mathematics had never before had to answer to that kind of practical demand of an instrument. In general, it had to be, well, the instrument is going to be tuned perfectly according to these ratios, as opposed to, we're going to now change what the meaning of number is in order to accommodate the needs of music.
Is it tuned by the rule?
Well, there was a huge controversy about, there was Aristophanes, an ancient musical theorist, who said things should happen through the ear. But he was the minority voice. The majority voice was Boethius and Ptolemy that said, like, no, it's got to be done through reason and through numbers. Only at this point did people start to say, we're going to have to let go of the need to, or the wish to have a kind of infinite specificity that corresponds to the ancient idea of knowledge, just in order to allow music to advance into this new kind of world of expressivity.
But, if you look at the ancient Indian music with the
Right.
it's actually more than half tones. I mean, they would look at 1/5, 1/7,
Right.
1/9 of a tone, because they have the sitars, which allow you to have frets.
Right.
Of any length.
And then you can slide.
I think that the guitar is asking is talking about. But in that sense, it's a much more sophisticated system than the Western system.
I think that's probably true.
It says it's any rational number can actually be portrayed in the Indian instruments. That's why for us it's so hard to understand or to listen to the music, because it has 1/3, 1/5, 4/5 of tones that are the common way of composing the ragas.
Right, and then the problem starts to be that if you then apply the music theory that only works up until the semitone, and start to push it further, then you start to get these problems of...
But in a sense, the music theory in the East did not develop very much, because the level of complexity of the intervals were so high that it's very difficult to make musical theory with arbitrary fractions.
Yeah, I think that's right. I mean, is that addressing your question? Because I think, I mean, this is in essence kind of a preface to what happened with Galileo, in which at a certain point the mathematical laws were going to be understood to be present in the physical world, but not exactly. But that they would still be present. The fact that the results that you got in experiment were never going to be in accord with the law was not going to falsify the law, as long as the approximation could be made as good as you want. But that was a very fateful decision that I'm trying to say is the only precedent for that was what had happened in music about a century or a half a century before, in which people have said, like, look, you're never going to get the number right, but it's going to be close enough. That was present for all these people, including for Galileo, whose father was a musician and was dealing with these things all the time. So in that sense, this is the prehistory and the prelude, maybe a kind of important or indispensable prelude for people to say, well, we're going to do this same thing with the physical world in general that we've had to do in music. We're going to have to allow approximations and still hold on to the mathematical laws, even though they're never going to be perfectly instantiated. So the second, I mean, I don't want to go on forever, but I wanted to talk in the second part of the what I was going to talk about today about a kind of parallel development of the concept of space that happened in 19th century mathematics. And the interesting thing here is that I don't think, even though people talk about Euclidean space all the time, or as a kind of background, there's no notion of space in Euclid at all. The word topos, which obviously is the origin of topology, just meant a place. And space was just the set of all possible places. But Euclid doesn't have a word. I mean, the closest word might be something like kora, which means country or something like that, or a set of all possible locations where cities or towns are. But there's no notion of an empty area which is governed by a certain kind of mathematical law. The idea of creating a generalized concept of space comes about, I think, in the work of Helmholtz especially, because Helmholtz is interested in trying to find out what are the differences between hearing and seeing. So let me just... Pardon? You have...
Space, a plane, hadra.
Right. You have a plane as...
Space, two-dimensional space.
Except it's not clear that it could be equated to our notion of a space. It is a plane area in the sense of level without any kind of rise or fall. But it doesn't have the sense of space in the sense of, even if nothing is there, we could speak about it. So that Euclidean space doesn't necessarily have to have figures in it. It could pre-exist as a kind of background. And we now understand it to have a certain kind of metric, a certain absence of curvature. You could talk about it in different ways. But the idea that you could talk about empty space, of course, was anathema to someone like Aristotle, who argued that true emptiness really has no being and is a kind of a paradoxical or nonsensical idea. So therefore, discussing the possible locations of bodies where there are no bodies was for them so problematic that there is no clear discussion, certainly no clear usage of the word space in Euclid, apart from words like plane or line or volume, where you're talking about solid geometry. But even solid geometry wasn't well developed, and the sense that there is something besides geometrical figures, that there are, tetrahedras or dodecahedrons is one thing, but for someone to say, and there is a kind of background space in which they're all immersed, that was not at all clear to Euclid.
The Bible, in Hebrew, shedach, it's now used as space, but as far as I now can remember, it's always used as just geographical kind of
Right.
plain area. But now it was a shedach, and it would be interesting to see where this transition happened. But now it's used, of course, in a pure geometrical sense.
Yeah, yeah. But for instance, it's very different to say that there's the plane of, I don't know what, a certain plane and a geographical plane, a certain area where the land is flat. And then someone say, and yes, and we can talk about like imaginary areas where there's nothing, but which is also flat. That's an interesting idea, but it was certainly, I don't think there's any evidence in ancient geometry that that was present for them in the way that is present in a modern mathematician's mind. And I think the place where it really starts to come into being is when Helmholtz is doing this whole series of experiments, first of all on the muscles of frogs, then he tries to isolate the human gaze and try to be able to stop the motion of the eye, or create these kind of really, I love this thing, in which he's trying to understand how the eyeball moves, because he had the idea that each position of the eyeball, as judged by the muscles that hold the eye, creates a certain sign. He had a kind of sign theory. And so what location really was the possible locations of the muscles and the orientations of the eyeball. But one can already see that he's trying to go from how the eye gazes to projecting out from that what we would call a space of the gaze. At the same time, then he was trying to do the same kind of thing for pitches and sounds and try to understand what was the relationship between the overtones and the timbre of the sound or the pitch of the sound, which at the time was highly controversial. Some people thinking that the problem of the relationship of the Fourier components of a wave to the whole wave, or in what sense they exist, or what exactly how they characterize the wave was not solved. And so Helmholtz had all kinds of experiments where he was trying to take the vibrations in time and to make them visible in space, like in this example of a kind of tuning fork. And then all the experiments that he did with sirens, he's a very simple siren in which the air kind of rushes through the holes. But depending on how the holes are spaced out, you can get a whole different kinds of sounds. So it was clear that there was a relationship between space and time. That is, that you could create a different sound by having a different geometric arrangement of the holes and for instance, in the siren itself. So the work with sirens is really important because it was the first moment in which the study of acoustics was decoupled from vibrating bodies. Because up until then, it had all been strings or flutes or bells or something like that. Suddenly it became possible to separate the two and to look, as it were, abstractly at what was going on underneath all sounds.
Visualize sound. Lightning Octaves, that was the first visual image of sound. That's why people were so impressed.
Yes.
Chladni who put it.
Yes, exactly. Chladni, where he has those plates, and
yeah.
That was also a very kind of important moment in which what was happening is that you were trying to reach between two different sensory modalities and understand that a certain sound was correlated to a certain kind of picture of the sand that you would scatter on the vibrating plate.
See what you hear.
You see what you hear, but it means that then you could build a bridge between the visible and the audible, and that they became capable of representations, that what was not visible could be represented, but that also meant that the aspects of the visible. Let me try to find an example. For instance, here's this example of, I think I've lost it, let me see if I have that picture of the color space. Because Helmholtz became interested in, I think I don't have the picture here somehow. He became interested in how you could represent the space of color perception according to Newton's views or according to the new view of color theory that Thomas Young had introduced and that he was also a proponent of. And that picture, I think I have it further, I remember it's further down in this right here. Here we are. Wait a second. I'm sorry. I'm skipping ahead of myself. Oh, here it is. There it is. So these are two different representations. Because the Newtonian space of colors that puts the more saturated colors near the circumference, but doesn't include the dimension of luminosity, which Helmholtz became aware of. And as he started to become aware of it, how you produce different mixtures of colors, he started to get shapes that were more and more non-Euclidean. And so part of Helmholtz's interest in non-Euclidean geometry was his realization that the space of colors, so to speak, was not a Euclidean space. I mean, that's the ancestor of this representation of how this projector is working, in which it's putting together red, green, and it's putting together these three dimensions of colors in such a way that it can transduce between numbers, binary digits, and colors in a certain kind of manifold. But the idea that it's the eyes, that even though vision seems to see a kind of Euclidean world, the way in which color perception goes is not a Euclidean thing, is something that Helmholtz was starting to realize. And the whole matter was it was very present, because of course Kant had only, in the century before, announced that the Euclidean geometry was somehow an a priori category of the perception of the mind. But now Helmholtz was starting to realize that, at least as insofar as color was concerned, it was not a that was not a Euclidean manifold. This led to all kinds of questions that he had to raise in his mind about, well, what exactly is the status of Euclidean geometry in relationship to the world? Now, and his work is part of this whole huge, go ahead, Nikita.
Relationship of the geometry to the world, or relationship of the geometry to the brain?
To the brain. To the brain. I misspoke. Yes, because, even though to the brain is actually more problematic, because if it's true that the brain is Euclidean with respect to spatial perception, it would be very surprising if it were not Euclidean with respect to color perception. And that's the thing that made Helmholtz think, like, wait a minute, what is going on? And he didn't really understand, and it was not very well au courant in his early work with the beginnings of non-Euclidean geometry in the work of Gauss or Lobachevsky and the others, Bolyai. This only came into his awareness later, but it's interesting that he discovered the problem started to trouble him as a result of this work in which he was trying to figure out the space of color perception in relationship to the space of musical perception, and in which the notion of space as a general category that could be poured different kinds, he uses that phrase, different kinds of content could be poured into it, and that it might that it could enable us to understand the modalities of the different senses. That seemed to be the place where the notion of sense, the notion of space had a kind of comes together with a particular force. I mean, I put the timeline here so that one can see that he's not really aware of Riemann until quite late. Let me just try to set up, so as I mentioned to you yesterday, Riemann in the last maybe 60, so he dies in 1866. During the period from 1860 to 1866, among his projects, this project about the mechanics of the ear, which is based on Helmholtz. That is, Riemann is aware of Helmholtz's work, admired it, but in the extent, the remains of his paper that were finally published, he said, Helmholtz's work is synthetic. He's trying to synthesize hearing out of the sense organs, out of his mechanical view of how the bones in the ear work. Whereas Riemann, want to create an analytic approach, and of course he's using Kant's terminology, an analytic approach in which he takes the whole functioning of the ear as a kind of black box, and then tries to understand how is it possible for the system to be performing in the way that we see to do it without it being without necessarily having to build it up from anatomical foundations. So that's a very, I mean, that seems to be the basis of the controversy between them. And the timing of it is actually quite interesting. Let me find this very interesting passage. I think it's earlier here. Okay. This is now, so Riemann dies in 1866. His paper on the mechanics of the ear is published in May of 1868. But the month before, April 1868, Helmholtz writes this extraordinary letter in which he says, my starting point is the following. What must be the nature of a magnitude of several dimensions in order that solid bodies, that is, bodies with unaltered relative measurements, shall everywhere be able to move in as continuously, monotonously, and as freely as do bodies in actual space? Answer. Let x, y, z, t be the rectangular coordinates of a space of 4 dimensions. So it's very extraordinary to me. It's not clear that time is that dimension t, but this is what he writes in this letter, which he then repeats, as I'll mention later on. This may be the first time in which some kind of space of 4 dimensions, presumably including time, if t is what it looks like it's being, what had ever been put forward in physics. And this is before he had read Riemann's paper. So in the aftermath of reading Riemann's paper, then he realized, oh, Riemann's been doing this work, trying to understand the foundations of geometry. In that paper, Riemann had said, the foundations of geometry are certain hypotheses. That's the title of this paper, on the hypotheses that lie at the basis of geometry. And the hypotheses have to do with the metric nature of the manifold of space. Manifold had been a Kantian term that then both Helmholtz and Riemann take up in a new way. For Kant, it had been, I don't know what, the assemblage of sensual information. But then for the two of them, manifold starts to take on its modern meaning. That is to say, a space which is intrinsically doesn't have content or order except insofar as it's been specified, either mathematically or physically in some way. So the next month after writing this letter, then Helmholtz becomes aware of Riemann's paper, which, you know, his paper on the ear, and he also becomes aware of his work, the 1854 lecture on the hypotheses that lie at the foundations of geometry. And Helmholtz realizes that, well, in a way Riemann is right, in a way he is wrong, because he feels that he's too much oriented towards hypotheses and not enough towards the facts of perception. And so Helmholtz writes a paper then in 1868 called On the Facts That Underlie Geometry. And the main fact for him is that rigid bodies are possible, their rotations have to be allowed, and that's what defines what physical space could be. That is to say, it's a physical criteria. And so, as a result of this controversy between the two men, of one of whom, of course, had died already in the meantime, and whose work had only become known after his death with a delay to the other, that's the basis on which Helmholtz was able to write down. I mean, then he takes this, it's interesting when he comes back after reading Riemann, after writing his reply to Riemann, in 1870, he reiterates the same thing as if he says, like, yes, I can see that Riemann understood more deeply what I was trying to grasp, but even in 1870, Helmholtz puts as a kind of appendix to his paper on the origin and significance of geometric axioms, this expression again, and he even allows t to be an imaginary number. So it means that he's already created basically a Lorentzian or Minkowskian kind of manifold. This is 30 years before Einstein, and before Minkowski himself. So it's a very, very curious thing. We do know that Einstein and his friends in the Olympia Academy read Helmholtz, read Riemann, These things were absolutely in the forefront of his mind. He was talking about them with his friends as he formed the theory of relativity. And yesterday, let me find this one little quote here. In 1899, he even writes to Mileva Maric, who was his girlfriend then, later his first wife, "I admire ever more the original free thinker Helm." He even sort of drops the rest of his name. So it shows you how young he was. I mean, he was then really in his 20s. He was still a kind of student at the time, hadn't finished his doctorate. He was imbued and steeped in these Helmholtzian ideas. And the quote that I gave you yesterday showed that he was very clear in his mind that what he did was a kind of reflected very, very strongly on what he had learned from Helmholtz and Riemann about the concept of space. So I think I'll just stop there and we could just talk.